Good morning, everybody. This is a short video to help you get started with Chapter 16. One of your classmates had brought up some questions about problem 16.1, and so I decided that I would set it up for you. So first of all, here on your Moodle page is the problem itself. Here we have a truck, and there's a uniform thin panel that is resting on it at an angle of 60 degrees with the horizontal. The panel's 5 feet long and the truck decelerates. So in other words, it starts to slow down, in this case, at a rate of 12 feet per second squared. It asks us to determine the reactions at the ends A and B and the minimum required coefficient of static friction at end A. All right, now the first thing is, it says it's a rough horizontal surface. That means that here at A, we have a frictional force. B is supported by a smooth vertical surface. B is therefore is not subjected to friction, and all of the force is just going to be the normal force between this vertical, whatever they're calling it, a vertical surface, and the panel. So here at A, we're going to have a frictional force and we're going to have a normal force. Here at B, we're just going to have a normal force. So the key to solving these problems is really drawing the free body diagram. And the theory that we're going to use, or the idea that we're going to use, is two things have to occur in order for that panel to not slide. One of them is that there cannot be any acceleration in the x direction. There also can't be any acceleration in the y direction, but specifically in the x direction, and also that there can't be any tipping here at point A. So in other words, we have two different ideas. We have summation of forces in the x and y direction, and we also have the moments about point A. So the most important thing for these sorts of problems is that you have to draw a good free body diagram, not a free good body diagram. You have to draw a good free body diagram, and you also have to take into account the inertia vector, or the mass of that panel, times the acceleration of the center of gravity, which is labeled as g. So every problem of this nature starts with a free body diagram, including the inertia vector. All right, so I draw this positive in the positive x direction. Whenever I don't know the direction of a force and I can't infer it pretty clearly from my free body diagram, from the situation, I draw it as a positive. It just makes the math come out a little bit better. Then once you draw that free body diagram, you want to make sure that all of your work follows the picture. So if you call, for example, the reaction at B in the x direction is negative, x, keep it as negative in your equations. The reaction at A in the x direction I've drawn as positive, keep it in that direction. That way the math will come out, and if you get a negative, you know that you have a sign reversed, but it's not a negative, which can look correct. So if you don't know better, always draw things positive. All right, so we have the force equations. Summation forces x equals mass times acceleration in the x direction. Summation forces y equals mass times acceleration in the y direction. So the first thing I do is I draw this equation where I have my negative rbx. I have my inertia vector, which is a force, essentially, which is equivalent to a force. And I have the reaction A in the x direction, that equals mass times acceleration in the x direction. For no sliding to occur, that acceleration in the x direction has to be 0. So the equation reduces to this, where the reaction A in the x direction I can recognize is a frictional force. All right, so I substitute in mu times the normal force at A. I then do my summation of forces in the y direction, which just involves these two, and I find that the normal force is actually equal to the weight of the normal force at A is equal to the weight. So I can substitute that into the equation, and I can come up with this equation. Now the problem is that I have two equations and three unknowns. I have the normal force, which I've determined to be the weight, and that equation, when I substitute it in, I still have RB, which is unknown. The mass of the panel is known. The acceleration center of gravity is known. Mu is unknown, and the weight is known. So I have two unknowns and one equation, which clues me into the fact that I need a third equation. The easiest or the best for no tip solution situation is that the summation of moments about A will be equal to 0. I could do the moments about any point, but A will eliminate the reactions at A from the equation. So what I do then is I refer back to my free body diagram, and the way I have it drawn, if I put a pivot point, if I put a pin here at A, I can see that the weight will pull it clockwise, the inertia vector will pull it clockwise, both of which are negative, and RBX will pull it counterclockwise, which is positive. So I set up my moment equations. There we go. So I have my weight times, since weight is vertical, it's the X moment arm, minus MA, which is horizontal, so it's a Y moment arm, plus RBX, which is horizontal, so we have a vertical moment arm, have to equal 0 for no tip to occur. All right, so in this equation, we have, and this is just RB, right? I can take this, I have this is known, I can find this from the geometry, these are known, find this from the geometry, and I can find this from the geometry. So my only unknown is RBX. I can solve for RBX, substitute it in here, solve for mu, which is the coefficient of static friction. In other words, the coefficient of friction that's required for this panel not to tip and not to slide. And then you'll have all of your answers. You'll also have your reactions. In other words, when it asks for the reactions at A and B, you've got the reaction at B. You can then find the reaction at A in the x direction because it's mu times NA. So you can find it from this equation. All right, so I hope that helps. Please let me know if you have any questions, and happy weekend.